this video I'm going to go through Math 2008 question 2, and for part 1 of this question they want us to find a pair of positive integers x1 and y1 that solve this equation. Okay, well we know that 2y1 squared must be even, and so if the difference between x1 squared and 2y1 squared is 1, then x1 squared must be odd. So if I call this equation star, then star tells us that y1 squared is a half x1 squared minus 1, just by rearranging to make y1 squared the subject. And so if we just look at all of the odd square numbers and look at a half of the number 1 less than each odd square number, then we don't need to go very far to see that actually a half of 1 less than 3 squared is 4, which is a square number. So if we take our x1 to be 3, then we get that y1 must be 2, because remember it has to be positive. And so 3 and 2 is a pair that solves our equation. Okay, so now we're given integers a, b, and we define two sequences, x1, x2, so on, and y1, y2, and so on, by setting xn plus 1 equal to 3xn plus 4yn and yn plus 1 to axn plus byn for n greater than or equal to 1. And they want us to find positive values for a and b such that this is true. Okay, so first let's call this star so we can talk about it later. And they've told us what xn plus 1 and yn plus 1 are, so let's substitute these two into star. And so we'll get this. So let's expand these brackets on the left hand side. Okay, and when we do, we get this, which simplifies into this. And so now we can just compare the coefficients of the terms on either side. So 1 comes from comparing the coefficients of the xn squared terms, and 2 comes from comparing the coefficients of the xn yn terms, so there's 24 minus 4ab here and none of those on the right hand side. And 3 comes from comparing the coefficients of the yn squared terms. So now we just need to find a and b which satisfy all three equations. So for example, I can solve 1 and 3 to find a and b and check to see that it works with 2. So if we used 1 and 3 to solve for a and b, we get a squared equals 4, and then taking square roots, a is equal to 2. Because remember, a and b have to be positive, and similarly we get b equal to 3. And so if we substitute a equal to 2 and b equal to 3 into equation 2, we see that we do get 0, and so a equals 2 and b equals 3 satisfies all three of these equations. And so these values of a and b satisfy our equation star. Okay, and now for part 3, they want us to find a pair of integers x, y, which satisfy x squared minus 2y squared equal to 1, such that x is greater than y is greater than 50. So this looks quite a lot like what we had from part 1. So in part 1 we were asked to find x1 and y1 which satisfied this equation, which we can see is of the same form as the one we're looking at now. But in part 1 we took x1 equal to 3 and y1 equal to 2, but now we're looking for x and y bigger than 50. So we're looking for another pair of numbers such that when we do this calculation, x squared minus 2y squared, we get the same answer as when we did x1 squared minus 2y1 squared. And so actually we can just use part 2 for this. So remember, from part 2 we had two sequences, and here I've just put the values of a and b that we found straight in. And for the terms in these sequences, when I do that calculation, we get the same as when we do the calculation on the previous terms. So if we started off with the x1 and y1 that we had from part I, and then use this to find out more terms in the sequences, then when we do this calculation on the terms that we find, we will still have 1. So we can use these sequences to find more numbers which satisfy this equation. So we can just keep looking for more numbers until we get ones that are greater than 50. So pause the video and try, see if you can find x and y using these equations. Okay, so if we use these recursive formulas with x1 is 3 and y1 is 2, then for x2 and y2, we have for x2, so it'll be 3 times x1 is 3, plus 4 times y1 is 2, so 3 times 3 plus 4 times 2 is 17. Similarly for y2, we've got 2 times x1, which is 3, plus 3 times y1, which is 2, so 2 times 3 plus 3 times 2 is 12. And if we use these formulas again, we see that for x3 and y3, which we find using these formulas, and x2 equal to 17 and y2 equal to 12. Then for x3 and y3, we have values which are greater than 50, and so we can take x equals to 99 and y equal to 70. Okay, and for part 4, they want to know what is the approximate value of xn over yn as n increases. Okay, so remember this is how we defined xn plus 1 and yn plus 1 in terms of xn and yn. And we also know that each xn and yn must satisfy this equation. So what do these tell us about the behavior of xn and yn as n becomes large? So if I say these are equations 1, 2, and 3, well, we can see from 1 and 2 that we're adding up positive terms. And so xn and yn are going to become larger and larger as n increases. Okay, so now what about their quotient? Okay, well, first we know that yn is getting larger as n increases, so it's not going to go down to 0, so we can divide by it. And if we divided 3 by yn in 3, then or if we divided by yn squared, then we'd get an xn over yn squared. And that gives us the quotient. And so because we've got the xn over yn which we're looking at here, then we can use this equation to see what happens as n gets larger. So remember, when n gets larger, then yn is also going to get larger and larger. And so 1 over yn squared, well, that's going to be getting very small. And so we can say that xn over yn squared minus 2. And so if xn over yn squared minus 2 is approximately 0, then xn over yn squared is approximately 2, and so xn over yn is approximately square root of 2, because we know that x and y are both positive.